Okay, welcome to the Ludii session. Ludii is a general game system that we're developing for the Digital Ludii project. This is a 5-year research project funded by the ERC, running at Maastricht for the last year and a half. One of the main aims of the project is to model the 1,000 most important traditional strategy games from around the world in a single playable database, and to reconstruct missing knowledge about ancient games. And Ludii is the tool that we're developing to achieve this. So the program today is 4 talks, 2 from team members Matthew and Eric, and then 2 from collaborators Cédric and Lianne on different aspects of Ludii. And then, if time permits at the end, we'll have a short demo. Okay, so the first speaker is Matthew.
Okay, so I'm going to be talking about my paper, Ludii as a competition platform, but I'm also going to be giving a bit of an overview about what Ludii is and how you can use it. So the outline for my talk is I'm going to say what Ludii is, for those of you who still aren't aware, then what Ludii can do for you as AI researchers, as game players, as maybe game designers. I'll then do a bit of a short live demonstration of the Ludii software. And then talk about some of the ideas that we have for competitions we can run using Ludii, and then finish with a bit of a Q&A. So what is Ludii? Basically, in 10 seconds, Ludii is a general game system for describing, modeling, playing, evaluating, reconstructing, optimizing, and generating a wide range of strategy games. We're mostly focusing on traditional board games, as Cameron said, but also card games, dice games, tile games, finger games, and even maybe some real-time games. So I want to start by saying that all the games in Ludii are playable by humans. This is not just an AI research testbed. We have a semi-nice, polished interface that allows humans to play these games pretty well, and so we're hoping for full international network play with humans, hopefully by the end of the year. But of course, we can also evaluate AI in Ludii. And so Ludii comes with several built-in agents that are included with the system, things like UCT, FlatMC, Generalized Rave. And so we can do things like performance analysis on these agents, we can do AI distribution visualization, and a bunch of other cool features. And so obviously we have a huge assortment of games. It's really great for testing the generalization capabilities of your agents. And we have a highly efficient system, which means obviously faster playouts and therefore better performance. So if you want to add your own third-party AIs into Ludii, it's really easy. It's really easy to integrate your own game-playing algorithms into the system. We have a really simple interface where, just given the current state and a forward model, your agent needs to return a move. So this is very similar to the framework used by the general video game AI competition. Currently, we only support agents in Java, unfortunately, but we will have support for other languages hopefully very soon. So basically, you just export a jar file containing your AI agent, and then you can import that file straight into the Ludii application. Just like any other built-in agent, you can access all the same things. And so programmatic coupling without the GUI is also possible as well. We also have the Ludii game description language, which we use to describe our games, and you can use it to create your own games as well. And so using this language, you can describe games in a really concise and understandable manner. These games are described in terms of what we call ludiums, which are basically units of game-related information, essentially the building blocks or DNA of the games that really encapsulate some sort of key concepts about the game. So for example, an equipment ludium might be this one on the left, which basically says that player 1 uses discs when they play the game. And you have a rules ludium example on the right, which is basically forming a line of 3. So here's an example Ludii game description for the game of tic-tac-toe. I'm not going to explain it all fully now. Eric's going to talk about that in the next talk. But just so you have a rough example of how a game description for something like this may look. Here's another example for the game of Hex. Again, not diving into it deeply now, but you can see they're fairly concise, well-structured game descriptions. So to really summarize just the main benefits of Ludii is that it's very simple. It's easy to define new games in a matter of minutes or even seconds using the Ludii game description language. It's a really powerful system. It's the only approach currently available to model the full range of games that we need for the digital looting project. The game descriptions are really compact, really small file sizes for these games. Each game can probably fit on basically a QR code. It's really comprehensible, human-readable instructions with a little bit of background knowledge. You can understand a game description fairly easily. It's a really efficient system. Our Ludemic chess, for example, is 10,000 times faster than an equivalent chess description from GDL. It's a really convenient language. It's easy to manipulate and evolve these games to create new possibilities. And it's also a really granular language, so you can break games down to their key concepts, label them with mathematical keywords or game-related ideas. So I want to do a little bit of a quick interactive demo to show those who still don't know what Ludii looks like. So this is the Ludii general game player. On the left you have the game board with all the pieces that might be on it. On the top right you have the player information, things like the players' names, their scores, maybe the things that they have in their hand. And then on the bottom to mid-right here, we have some information and analysis about the game that's being played. So like things like whose move it is, the rules of the game, this sort of thing. So here we have the game chess. I'm hoping most of you know the game of chess. Basically, you can play this game yourself, just by dragging pieces around the board, selecting them and moving them around. Like so. And obviously the game will prevent you from making any illegal moves. We can do things like showing the possible moves that the player can make. So blue dots here represent the pieces you can select, with the red dots being where you can move those pieces to. Like so. We can also show the last move that was made. And a bunch of other things like this that just improve the quality of life for humans playing the game. If you want more information about the moves, you can find them here in the Moves tab on the right. So this is the sequence of all the moves that have been made so far in the game. Basically, moves that have been made, and then also how the state of the game has changed as a result of those moves. You can go backwards through this to view and return to previous states of the game. And you can also save this sequence of moves, meaning you can easily save full playouts or save a particular state in the game that you want to return to at a later point. If you're into customizing the graphics of the game, we have some features for changing the colors. You can make some pretty terrible color combinations should you wish. Let's see if we can make it as hideous as possible. If you're really into doing that sort of thing. Let's go back to normal before anyone takes pictures. So we currently have 100 games in the Ludii system at the moment. They're organized by their mechanics of play. So, for example, the game of Hex, if you're familiar with that game, is a connection game. And so for those of you who aren't familiar with this game, basically each player takes turns putting pieces of their color down on the board, with the goal being to form a connected path of your colored pieces between the two edges of your color. And so we're going to use this as an example to sort of show off just some of the agents and the AI algorithms we have with Ludii. So we can set up a game, for example, between a UCT algorithm, maybe a generalized Rave algorithm. We can give the agents a bit more thinking time, so it doesn't end straight away. And if I hit play, you can see the agents are obviously starting to play the game. We can also show some things like the AI distribution. So here we are actually visualizing how the AI is thinking about its moves. So you can see that there are these dots appearing on each of the places that the agents can play. And basically the size of the dot indicates how much the agent is thinking about playing there. And the color of the dot represents whether the agent thinks this is a good or a bad move. So blue if it thinks it's really good, red if it thinks it's really bad. You can see that UCT is a lot less focused than MC Grave is, sort of playing all over the place. And now we can see that UCT seems pretty confident in itself. Although I'm not certain if it will win. I'll let that play out while I keep going. If you want even more AI analysis, you can find it on the Analysis tab here. So you can see things like the number of playouts that each agent is achieving, the predicted value of how likely it thinks it's going to win the game. That might take a while. We also have each of our games also has several options usually for changing things like the size of the board, or maybe the ending conditions, or the number of players. So for example, if I wanted to go to a much smaller board size, 6x6, easy enough to do that. And yeah, so that's just a little quick demonstration of some of the capabilities we have in Ludii. We have many more features and many more stuff that I won't go into now. But pre-release, the beta version of that software that I was just running just there is available now. You can all go and download the software at our website, www.ludii.games. Like I said, we have 100 games at the moment. The entire program for running this is only 3.5 megabytes. In fact, it's slightly under that. And this includes all the games, all the graphics, all the AI that's needed. So please try this out. You can just play a few games if you want, or try some of the agents and give us some feedback on whether you think this is good. Any feedback or comments would be great. And it's still incomplete and subject to change. We will refine some aspects of the game, so it's not fully complete yet. The official public release will be coming 1st of January next year. And we're hoping for around 200 games by then, if we work hard. And an Android version will be coming hopefully very soon. So I wanted to now talk about some of the competition ideas that we have for Ludii. And so I'm going to break these down into agent-based competitions, PCG-based competitions, and then just some other general competition ideas. And so most of these competitions can be done using either or both AI and human players. So in terms of the agent-based competitions that we're intending to run, we have several variables here that we can change based on the capabilities of the agents we want to test, and also just general interest of the community. So the first thing we have to look at is the game source, where these games come from. Are the games that these agents are playing known? Do you know which ones they're going to be trained on beforehand? We're going to test you on these 5 games here. Are these unknown games? So the entrants may be given access to a huge set of possible games, say 1,000 games, but they don't know from this large set which small evaluation subset we're going to use for the competition. Or are these brand new games that have never been seen before? We've made them specifically for evaluating the agents, and they have no idea, they've had no time to look at them beforehand. We can also look at the types of games that the agents can be able to play. Is this a no-holds-barred competition where any type of game is possible, card, board, dice, doesn't matter? Or is this just focusing on a specific subset of games? So maybe just deterministic or stochastic games, maybe just hidden information games, or any of these categories down here. We can also think about the number of agents that these games have that are used in the competition. Are these multiplayer competitive games where 2 or more agents compete against each other? This is probably the most common type of board game. Are they multiplayer cooperative games where the agents have to work together to achieve some goal? Or are these single-player puzzles where there's only you and you have to find a solution? We can also look at the information that we provide to the agents. Do these agents have a forward model, as is standard? Perhaps they do, it's very nice for them, but maybe we only give them the game description, and they have to understand how to create their own forward model from just the rules of the game. Or maybe we don't even give them that. Maybe we just say, here's the game, we know the rules, figure out how to play. We can change the learning time that the agents have. So most obvious would be give them no learning time. You have no time to train for evaluation, you just give them the games and let's see how they do. But maybe we do give them a small period of time beforehand where they have this access to the evaluation games where they can train on them for a little bit before they're actually evaluated. Or maybe we can even give them different but similar games. So we might give them the same game but with a different board size, or a different board shape, or maybe different starting positions. And they have to generalize from that to the same rules but with a different initial setup. And the last thing we can look at is the competition format. So would this be an elimination-style competition with knockout-style rounds, a round-robin competition where you play against all the other agents? Maybe it's a bit longer, maybe it's like a leaderboard that we continuously update over several years even, or a league that we run that lasts several weeks or months. And so these are all the possibilities. So it's really great, hopefully at the end, to get your feedback on which of these you think is the most interesting. If you have any other ideas, please do talk to us. So for PCG, content generation competitions, we also have some variables we can adjust. So we can look at what we're actually generating. Are we generating the games, a complete game with a full valid game description? Are we generating, if we're doing puzzles, say, an example puzzle from a given rule description? Are we generating maybe just the rules of the game, given the equipment we have? You have this board and you have this pieces. What rules can you come up with using this equipment? Or maybe even things like the instructions for a game. Can you generate human understandable instructions given a Ludii description? Essentially a plain text English generator. We also have the generation requirements. Is this a free-form generation where you have just generate whatever, we don't care, free-form completely? Maybe we give them specific Ludii that they have to include in their game. You have to use this specific Ludii in your game description. We can also do this, essentially the same thing, but we're calling it partial evidence, which is the same, but this is based on actual historical information. So we know that perhaps you have this board or this particular rule, and we have some incomplete information based on historical and archaeological evidence, and you have to generate a game using this information. And maybe even something like deceptive games, where we have to generate games that agents find specifically hard compared to, say, human players. And then the last thing for PCG is always how you actually evaluate the generated content. Do you just use a team of highly specific selected judging panels, human judges? Do you use agents to evaluate the content in some way? Perhaps for things like the fairness of the game, how complex is the game, how long does the game last? Does the game usually end in a draw or not? Or even just a public vote. Open it to the huge game community on the Ludii application and say, hey, rate these games, see which one you like the best. In terms of a bit more other competitions, a bit more out there ideas, we have the Turing test idea, where agents have to play in a human-like manner for their games. We have a generate and play competition, where you have generators and agents actually competing against each other. So the generators are constantly trying to create these new games that the agents find hard, and the agents have to learn to adapt to those generated games. We have competitions like Needle in the Haystack, which actually the agents submit the game evaluation software. So we give the agents, the evaluation systems 10,000 randomly generated games, and they have to evaluate them and try and pick one that they think is the best. Even something really wacky like QR code design, where as our game descriptions can fit on a QR code, perhaps we can create some custom QR code style graphics for the games that we generate. And like I said before, we're open to any other suggestions that you have, things that you think could be really interesting using the Ludii software. Really hammer it home again, Ludii.games. The software is now available. Please just download it, give it a go if you want. Give us some feedback if you have any comments. And that's it. Thank you very much.
Yeah, so thanks. So I would like to start that really admire your work, especially the GUI, which is very nice. Only one comment to the GUI, you made this type of game. Please make a field to just type chess and find whatever
you actually have that functionality already. We just don't have a search bar for it. So if I type in chess here.
Oh, so it's not
you don't have a search bar yet, but you can search for the game just by typing it.
So the question part of my comment is actually, did you think what kind of conference you try to fit in this competition? Like you aim for AAAI, or which covers CIG, CEC? Do you have some kind of more concrete where and with what you want to go? I know it's a bunch of ideas.
We're still thinking about the idea. I think we would like to perhaps run just a standard agent competition at CoG next year, to start with. But of course, we have all these possibilities, so it depends on community interests. What are people more interested in? What can we do to help in that regard? So, yeah.
So about the interest, do not start with all these competitions at once.
Of course.
I really think that the PCG thing will be very interesting because it's not much to compare in here. Video, but it's hard. And I really love this Needle in the Haystack idea. Because this actually makes it's PCG competition, which is not PCG because you want to try find a filter, so evaluation metrics. And I think this is a really good and nice idea, which I didn't see before in any these type of competitions.
It could also be useful for the computer Olympiad at the ICGA.
Oh yes, ACD also is it, yeah.
Very interesting work, yeah, great work. Two questions I have. The first one is you showed shortly this Ludii GDL, and it has some resemblance, but what is the difference to GGP GDL?
Eric is going to get into that in the talk just after this, comparing the different game description languages, so please wait 5 minutes.
And the second question is you spoke about highly efficient systems that you make. what does it mean in moves per second?
Yeah, it's basically the playouts that you get from running that. Again, Eric is going to talk about that just in his next slide. So hopefully, if you still have questions after that, maybe raise them.
So in contrast to GGP, you are not have not an interpreter, but you compile it somehow. When agent is compiled, and can be so efficient as an agent in Java is. Basically.
Yeah, we compile directly JavaScript level, so we can run our playouts directly from Java. Java is the Java distro language, but it's hidden with our function. You will see that in some minutes in my slide.
Hi. Congratulations for the work, for everything. All the games that you are showing in this program have been written using the language?
Oh, perfect. Eric mostly wrote the language. He is the expert behind this. I know a little bit about the language, yeah.
How easy is to add a new game?
Sorry?
How easy is to add a new game?
How hard is it doing? Depends how complex the game is. It's pretty easy to take. If your game is very similar to an existing game, then it's easy to take that game description language and edit that to suit your needs. Eric is actually going to be giving a demonstration at the end of generating a game completely from scratch. So, again, I would pass it off to him.
Thank you.
Yeah, sure. Okay, just a quick question about the GUI. Mm-hmm. So you showed us that beautiful language, it's very concise, and then you've got this beautiful GUI.
Thank you.
I'm guessing that didn't happen by magic. So if you write a game in this language, what would the GUI look like?
So we have existing components for things like the knights, say, or the rooks, and we have all these images for those particular pieces.
Which is great.
For chess, which is great. But you could take the knight piece and change the rules for that piece to work in any other sort of situation. Okay. So the graphics and the game description language are linked in some regard. Like, for example, this is a chessboard, because it looks like a chessboard. But you could create, if you wanted to just define it a bit differently in the game description, you can do that. You have the flexibility to define new stuff. But we also have some existing templates for existing pieces.
For example, for the board, we have a generic Lianne just called board. And from that, you can define the shape and the tiling. So you have any kind of board you want, but without wheel. It's just a background blue with some edge. But if you want to use one of our custom board, for example, that one is a chessboard, we have a Lianne just for that. It's paginated.
Yeah, so say I'm not really interested in the GUI at all, I could just describe the game and it would give me some sort of GUI that I can see. But it would,
you will see at the end when I make a game from scratch from nothing.
Yeah, the GUI is separate to the logic of the game.
Yeah.
Yes.
Quickly, can you find, from your GUI, can you look up the game description for chess first?
Yep, just hit. Under Ludii.
Oh.
There you go. Yeah. We do have a user guide for the application as well, which is also on our website. So if you're struggling to find something, have a look on there. If it isn't there, just message us and we'll help you out.
In stock, the game description has not finished currently, so we have to improve that again. For some games, it's a bit hard. For example, don't look strategy.
Yeah.
The game description is really.
We will optimize this for the full release. So, yes.
So, the games that you've shown, maybe that might go back to your talk. But the games that you've shown,
take all the questions.
Are really, they're two-player alternating Markov games, right? So they're very standard two-player games. What if you have multiplayer games for observability? You mentioned these things.
Yep. At the end, we can do a quick little showcase of all the games we have. We have simultaneous move games. We have hidden information games, partial observability, n-player games, single-player puzzles.
Stochastic games.
Stochastic games, yes, of course. Any games with dice, of course, stochastic. So, yeah. We can do a little quick showcase at the end. Yeah. Okay. I'll give it over to Eric.
So let's go for the French accent. So sorry for my accent if you don't understand me. I will do my best. So yes, in this talk, I'm going to show you a comparison of our system, the Ludii system, and another system, the regular board games. Of course, here I talk a lot about general game playing, so just a quick remember. In general game playing, we want to create a generic artificial intelligence working with many games of different kinds, different types, not a specific one. But this is not the only goal. There are some other goals beyond the general game playing. One of them is to create a general game system easily usable by any human to play, to evaluate, to generate, like said Mathieu on this talk. And also to reuse all the algorithms we make for general game playing to some other field, like the game design, of course, education, history, for example, with our project, or robotics. For all of this reasons, the general game system have to answer to some criteria. Three main ones are, for the game description language, the clarity and the simplicity of the game description. So the clarity is the capacity to understand directly the rules if you read the game description without refer to specific knowledge. So without, for example, to know a specific kind of programming, just you read the rules, you can understand them. Another criteria is the simplicity. Simplicity is just a synonym for us to short description. For example, if you want to model a simple game, we want to keep that really small, because if you want to model later a more complex game, if for a simple game this is already long, this is again longer after, so just impossible to read, it's hard to do. And currently the best techniques for general game playing is MCTS. It's based on the number of playouts. So of course we want the maximum number of playouts per second for all the games with the general game system. So we need that three criteria for any general game system. The current academic standard is the well-known GDL, so game description language, is based on logic programming of the first order. So you have here a game in a GDL. So if you are not usual with this game, I'm not sure you can find it easily. So I will tell you, it's tic-tac-toe. And even if I say that, if you try to find why is defined a line on that, good luck. Define it. So after this language exists since 2005, so since 14 years. And if you look in all the repository, if you count the really different games, you have only 52. So after 14 years, it's not a lot, and 3 of them are incomplex. So here I count just the real board games. I don't count the different variants or the special file done just to test the language, just the real board games. And if you make a new game with GDL, you don't have directly an interface. So you are not sure if your description is good or not. The only way to make an interface, and not for everything about GDL, is to create an XML file on lab in a web interface. You have a part of your interface, but not all. So no interface. So you can look, that file is half the description of X, so the game I explained much just before. Again, hard to read, hard to, if I don't say to you it's X, I'm not sure you can find it. And really long, not clear, not simple. Maybe I can show you a more complex game. Again, like say Mathieu, logically everyone knows chess. So maybe I can show you chess. No, I cannot. It's really too long. More than 4,000 tokens to describe chess in GDL. So in my computer it's more than 20 pages of logic programming. So good luck. And if you want to improve it, to fix it, if you have a problem, this is really hard. Sometimes it's just impossible. If you want an example, I make all my PhD on this language. I make something like 2 months to fix one bug in a GDL file. So really hard. And the source is not efficient because with a language like that, if you want to model the state differently, you need to interpret it and to compile it. So with the best interpreter we can find, one of the best, done by Chiara, we get only 0.06 playouts per second for chess. Not enough to apply MCTS on it. So we need something else to GDL. Something else is necessary. So here I'm focused on 2 of them, 2 of many of them here. RBG, where the game are described with a regular language, and Ludii, where the game are described by Lianne. So Lianne was explained by Mathieu before, so I don't explain that, but I will explain after works a bit RBG. And the question here is, which is the best alternative? So of course RBG can again evolve, I'm sure, and Ludii evolve also, because this is also, currently this is only the pre-release, it's not the release, so we want also to improve. So this is a preliminary comparison between the 2 languages. So GDL vs Ludii vs RBG about clarity, simplicity, and efficiency. Ludii. So you use the regular language to encode the movement of the pieces. They can describe the full range of determinist board games. So this is the same full range of games than GDL. So they can model the same kind of games. They have two levels of the language, one low, one high. The low level is given to the input of the programs and easy to process, so efficient if you run some playbooks on it. And the high level is done to be more concise and more readable by any human. So here you have the high level. And of course, you can translate the high level to the low level in order to optimize the efficiency of your approach. Thanks to the modulation, you can model more complex games. Some games almost not done, just not done in GDL, like chess, Go, or Arima, because chess was like that in GDL, and Go in Arima was completely not done, so there are more complex games. So that file is a complete description of the same games as before, tic-tac-toe. This is, I think we are all agree, this is fairly clearer than GDL before. You have here the initial state of the game, so this is the board of tic-tac-toe. You have the tiling, you have the player, the first line, you have the pieces, and here the rules are defined. So this is clear, but you need to know the regular language to understand the description. Of course. So it's for us, it's a computer scientific perspective when you model that. Now I will show you the same thing in Ludii. So I can explain just a bit. So in Ludii we use the Lianne to describe games. We can model any game modelizable in Java. So determinist or not, hidden information, simultaneous or real again is possible. Our grammar is completely generated automatically from our classes in Java. We can easily manipulate to evolve again. I will show you that just after. We have all the graphical interface as shown by Matthew during his talk, and also at the demo at the end. It's going to don't explain that, he already done. And we can optimize each of them in order to get the best way to compute each evaluation of each student. So, just to explain how that works, here is again tic-tac-toe, but in Ludii. In our description, we have the name of the game. Here, we describe the number of players of the game, so 2 players. Here, we define the equipment in the second part. So, here it's a board. It's a square board of size 3, tiling by square. So, square size 3, tiling by square. For the player 1, you have a disk. There, and for player 2 you have a cross, there. For the last part, we define the rules of the game. That part defines the concrete rules of the game, so the playing rules during the game itself, and thanks to that you will get the legal move of each turn. So in tic-tac-toe this is really easy. If you are the current player, you can put your pieces to any empty site. And you reach a terminal state if you make a line of 3, and in that case, the result, the current mover, win. So in our description, this is the game designer perspective. Exactly like if I want to explain to you how works a game, I explain like that. In our description, you can read that directly. So this is another way to do that. And the goal of this paper was to compare the different way between RPG and Ludii. So for clarity, I cannot provide to you some metrics because clarity is specific to each people. Some people prefer to use a game design perspective, some other computer perspective, and if you are crazy, logic programmer, for example. So you have to make your own opinion. So just to show you another game in RPG and in Ludii, I can give my opinion, but this is not something generic. You can make your own opinion, of course. So here you have again X in RPG. So the initial state is nice. You see directly the board itself. The E is to say this is empty at the initial state. You have the tiling there of the board, the shape of the board is there, and the rules are described here. So you have how you define the neighbors, what is the turn and the rules on it, and how you reach the different pieces. So again, according to me, this is clearly better than GDL. I think you are all agree with me. But you need to know how it works the regular language to understand mainly that part. With Ludii, again, we can describe the rules directly, like I would like to explain to you the rules. So Matthew explained the games during his talk. I can do exactly the same with Ludii. So it's a game of 2 players. The equipment, it's a board of a ground boost 11 by 11, tiling by X. We have a ball for each player. We have to define the region for each player. For the player 1, this is the edge of the board of the northeast and the edge of the southwest. For the player 2, the edge northwest and the edge southwest. At each turn, you play like a tic-tac-toe to any empty state with your pieces. And if you connect the region of your region, the result of this mover is to win. So this is exactly like we understand the rules, the closest possible. So, of course, if you ask my opinion, to me, Ludii is clear, but this is one opinion of one member of Ludii, so of course, I prefer that, but you can make your own opinion. At the end, just before the demo, I will make from scratch this game, Amazon, in live from you, in front of you, because it's one proof we can build any game in maximum some minutes. So we will see that from nothing, I will make Amazon, because it's really, really easy, exactly like we understand the rules. So I'll keep that for the end. Let's talk about simplicity. So simplicity is really easy to understand. This is the size, the number of tokens to describe a game. So you have here a list of games available in Ludii and GDL. In the second column, the number of tokens you need to define the game in Ludii. Third column, the same thing for GDL. And last one, the rate. So if you look at the rate, we are always under than 13%, and in average under than 10%. So the discussions are way, way smaller. This is very simpler to do that. We can do the same thing with RBG, but just before, if you compare RBG and GDL, of course RBG is always smaller than GDL2. Clearly, because regular language is clearly simpler than programming. So, but the goal here is to compare Ludii and RBG. So some games are available in Ludii and RBG. Same thing, one column for Ludii, some column for RBG, and the rate there. So if you look at the rate, Ludii is always shorter, but this is not the same gap as GDL, of course. Sometimes we have some close to 60%, and sometimes 6%. So sometimes we are simpler, but not with the same gap. Now, I talk about clarity and simplicity for the language itself. I would like to talk about efficiency. So for the efficiency, this is the preliminary result, like I said at the beginning. So this is our version from this paper, not the version of the theories you have online. So that's exactly the same. And for RBG, this is the version of the triple AI, not the last version. So you have the same thing. You have the number of playouts per second in the second column for Ludii, and the number of playouts per second for GDL on the third column, and the rate in the last one. If you look again at the rate, we are clearly faster. The best one is chess. We are 18,000 times faster. For X, more than 100. For some others like Amazon or Goku, again, really faster. So for all of them, we are all the time more than 2 times, and sometimes really, really faster than GDL. Because we can optimize our rhythm, like I said. If you do the same with RBG, with the 2 versions we have, sometimes we are better, sometimes not. If you look in black, the rate is specific. Say we are slower than the RBG, and in red we are faster. But in general, we are more faster. Sometimes for IMA, we are really, really faster, more than 6,000 times. For Gomoku, close to 20. Sometimes this is really equivalent, 1.03, 1.01 for chess and chain checkers, for example. And for some exceptions, like breakthrough or English checkers, so for breakthrough, RBG is 4 times faster, +2, and for English checker, +2 times faster. So for efficiency, we have different kinds of results according to the games. So just to sum up, for all the criteria, RBG and Ludii clearly better than GDL. For all of them. For clarity, hard to say something. For Ludii, we have a game designer perspective, so we try to define the game like we understand them. And for RBG, more a computer scientific perspective with a regular language. So it depends what you prefer. For simplicity, according to all our results, Ludii is better than RBG because it is always smaller. For efficiency, depends. For most games, Ludii is better, between 2 and 6,000 times faster in this result. That can be changed because with the release, we want to run everything with the release version and the last version of RBG just to be sure of this result. Sometimes Ludii is equivalent to RBG, and for some exception, for 2 games in our experiments, RBG is better between 2 and 4. So, logically, my paper is done there, but I want to use a bit time to talk just a quick overview how it works Ludii inside. So, Ludii inside is 4 modules. Well, the first one is a AI module with all our default artificial intelligence on it. So I think I should say that. We have UCT, Grave, Bias FCTS, also it's another version. We have different kinds of AI. For the release, we will add more. But we can also add your own AI, like say, the second module is a grammar. This is one of the more important. Thanks to that, we can generate automatically our grammar. So for example, equipment, mode, game, chessboard, all of them are written. And we can generate all of them from the different classes here in the library. Because the library is all the LUDEM structured by the class hierarchy. So on it, if you have one class, that file is a LUDEM. So grammar generates all of them against the grammar. I will explain that just after. And grammar is also really important because it can compile all our game defined in LUD file to an executable in Java. And this executable has all the stuff you need, the state, the representation, the Java classes, the evaluation, the interface. And the interface is linking by the last module, the player module. You have all the controller for the graphic interface or the command interface, and all the work between them two. So for this part, you have a huge demo of Matthew just after. So he explains it. So just I have the time to explain a bit how it works on compiler. So for the compiler, we use the class grammar approach done by Cameron in 2016. We generate the EBNF grammar from all the constructors of each classes in the library of LUDEM. Thanks to that, the game instances are expressed directly in our grammar, and we can compile all our games by calling the relevant constructor. So if you I have an example. So here you have again tic-tac-toe. Here, if you look at this file, each word, that word, all the words are LUDEM. And this is the name of the constructor of each classes corresponding to each LUDEM. So we call them during the compilation. And if you have some parameter like that, this is the parameter of each constructor, and we can build by reflection with Java directly the executable. The benefits of this method, our grammar is automatically generated from the code, so we don't have to maintain this grammar at the side to the library itself. We hide completely the implementation, so we don't have to know no skill in Java to create a new game, and we offer all the full functionality of Java without to use Java. If we want to add or modify any code in the library, we automatically incorporate in our grammar. So Java is our game language, but we hide all the stuff you need to know to use Java users. So just quick explanation about how the state operator works, because I need that for the next talk. We have different kinds of information for any games, and we create some slab of memory of each of them. So we call that struct set to describe what is on each site, who is the owner of this site. So we have each struct set there to describe each information we need for each site. And we split all of them in regular struct set to encode the data. So for example, for our 2-player games, the struct set who use only 2 bits, because it's a big board, to describe them. So we have 4 kinds of information, we can model them only with 2 bits. And we keep something, the struct size is always the power of 2, the smallest power of 2, in order to be more efficient and to use only some binary function. That's why we try to keep something smaller than 32 bits, the size of a long, because we can use directly some binary function on it, to be faster. It's one of the causes why we get some really huge number for all the players. And so we have different kinds of sets according to the game. Ludii detects automatically if we need to use a specific state or not. For example, here you have a stacking game, so we need to know what is for each site, but also for each level, and how they are organized. So in that case, Ludii detects automatically we have some LUDEM referring to a stack, and we use a stack stacking. For chess, we don't need that, so we don't use a stacking game, we use only states for each site with what PC is there and who is the owner. And you will see in the next one, we have a specific case for the puzzle. I explain that after. So that was just a quick overview about Ludii. So if you have many questions, we want to know more, ask me. Thank you.
Okay, so I sadly have to play a bad cop here because I'm one of the authors of RPG and I want to raise some questions. To make me concrete, I will focus on efficiency only. Issues that from all the games you've shown from this table, only 5 games are correct. Like for international checkers, you have wrong rules because Ludii game code allows not the longest sequence of countries. For the Arima, the game for the true game branching factor for the first move is 40,000. In your Ludii, is 40 because you split moves, and so it's not the same game tree yet. And for all, Also, because of that, you cannot check like no repetition move. So this is a different game. Similarly, you have a double chess here, yes. So for double chess, you compare your simply king capture version.
No, it's not. If you look at the version in the theory,
You updated the version for the king double
it's
chess
not,
also.
yeah.
Because in
the version is not the same game.
okay.
For double chess, for the others, yeah.
So the case is that you use split in all your things, and in some cases this only means that you're faster because you compare on a different game tree, which is not fair comparison. And for some games, as I mentioned, Arima, for example, and international checkers, this simply means you have totally different game rules, which is from the standard. And that's kind of this.
Okay. I think you would say the same for Amazon. For Amazon, if you split or not, of course, the game tree is different, I agree, but the rules are the same. So your modelization...
Okay, but you do not compare the rules, you compare the efficiency.
Yeah.
If you compare the efficiency on two different trees, you cannot say you're comparing efficiency from the search perspective. Yes, so this is, I simply claim this is unfair comparison because you use different trees for both approaches. And in some cases, we're not talking about like small kind of a differences, but in some cases these differences are huge. Okay, we see an Arima, like computing a list of 40,000 moves to just make possible legal moves and search through MCTS or playing Monte Carlo or whatever. It makes far more huge effort than compare like 40 moves 4 times.
Can we discuss this afterwards?
Yeah, we can cover this afterwards, but as we will sending you a bunch of emails about it.
Yep.
I wanted to raise it.
Yep, thank you. Any other questions?
When you speak about playouts per second, does it mean a whole game or a single move in a game?
No, it's a whole game. The random playout from the starting, the initial state to the any...
complete episode.
Yeah. The random one. Is what you need to run any CTS on it, because from that you can...
And another question was, you said from the Ludii game description, it's automatically the GUI compiled. Was it on some of your slides?
The what?
Huh?
The compilation? Sorry,
The GUI is from the rules, exactly.
The GUI is generated from the rules automatically.
Yes.
If I, for example, have never seen chess before.
They're generated from the equipment Ludii. Each piece of equipment knows how to draw itself, whether that's rendering itself in native graphics or loading an image.
So you have to define the proper Ludii. That's what I mean. I mean, when you make a new game where the first time appears a tower like in chess,
that's right. Yeah.
Then you have to generate a tower, of course.
You have to either generate or find an image for it. Yeah.
So lots of the games that you've talked about are classic games. Have you got any like modern games? I don't mean disparaging, but like games in the past sort of 6 or 7 years as board games in your framework?
Stratego?
Yes, we have Stratego.
I think you just mean more complex, as in the dynamics, or just because there are many modern abstract games that.
Oh, with things like Forbidden Desert, not Conan, but things like that. So Carcassonne, that kind of thing.
I don't think we have. No.
Okay.
The focus is mostly on the historical games.
In theory, it's possible, yeah.
In theory, it's possible, yes.
At the end of the 5 years of the project, we hope to model, of course, a way bunch of games, so that game, why not? But not currently. The priority is really the beginning.
And unfortunately, the more recent board games tend to be much more complex, so getting a UI that handles everything generally.
Since we are in the Queen probably you know that the Queen has a platform, GBD
like platforms. But I think it's more or less the same.
Which platform?
The GBG AI platform of Diego and company and Simon is more or less the same, I think.
Similar. We actually do support real-time games, so there's some overlap between them.
And which is the difference of the previous one?
I'm not an expert on GBG AI, but it's focused on real-time video games. I don't believe it supports the games that we're looking at.
If you try with VGDR, if you try to model chess, for example,
there's a lot of restrictions on VGDR. You have to have an avatar, you have to have something, so it's clearly geared towards a simple arcade style video. Not so much.
The difference is the type of games.
Yeah, like I think in GPG AI, you've always got like at most 5 actions. It's always an avatar that's being controlled with like 4 movement actions, sometimes a shoot action. You could never do like hacks with that because there is no avatar. You've got actions all over.
Then the question is that this kind of game cannot be in the GBGI and the GBGI game cannot be in this platform. There are 2 different platforms.
The GPG games could be in Ludii. But not, it's not the focus at the moment. We do have some simple real-time games like Tron, for example, and Snake and stuff like that we can do in the
Ludii. You will see Tron and Arcadian, but it's just a proof of concept, just to show we can do that. But this is clearly not the goal of the project because we are focused on choice audience and video games.
Yes, okay, thank you.
Thanks, Eric. The third talk is from Eric and Cédric, and they'll be talking about modelling puzzles in Ludii.
Okay. So we are now speaking about a more specific topic because it will be only puzzles, so one-player game. And I have to introduce myself. I don't work on games. I'm not like you guys. I work on constraint programming. Games is not my main topic of interest. And we use actually constraint programming to solve puzzles in Ludii. But first, you may want to know how in Ludii puzzles are encoded, are represented, and I'm not the best person to present you that. So, Dr. Piette.
Just take 5 minutes to explain how we define our specific state for puzzles, for logic puzzles. So logic puzzles here is defined again by the check set you saw just before. But we have one check set according to the vertices, the edge, and the faces, because all of them are more easy to describe a puzzles. For each check set, for each possible value you can set to these variables, they are only Boolean. So if this value is equal to 0, you cannot set this value to this variable, and if it's equal to 1, you can set this value to this variable. For example, for Sudoku, we have 81 variables, 1 for each side, because each side is a vertices in the graph, even if the graph is not necessary, you have the graph in Sudoku. And for each side, you have 9 possible values, 1 to 9. So for example, if you want to set a value to a variable, your checks, for example, here for the variable 10, this is a vertices. If you want to set the value 2, you have to set this check set. So for all the value all equal to 0, except the value 2. So if only one value is setting to 1, this value is set to the variable. And in our modelization, the puzzle is solved when all the variables are set to one value, because you have only one possible value for each variable. That's why we provide a constraint model. So because the logic for puzzles is a problem satisfying a set of constraints. For this reason, we have one readline called constraint, and on them we can model all the constraints of this problem. For example, and this readline constraint generates all the legal moves of the puzzles and correspond to setting a value to a variable only if this value doesn't violate the constraint. So for example, here for Latin square, the rules of the game are really easy. For each row or each column, all the values have to be different. So if you look at these cells, you have on the row 5 and 4, on this column 3 and 2. So for these cells, the only possible value to set is 1. So all the small numbers you see are all the possible value you can set to each set. This is done automatically by our set representation. Of course, we want also to keep something simple and clear for the description of the puzzles. So in a lot of puzzles, you have some hints at the beginning and some specific region. So for many puzzles, we can define directly in the initial state the different hints of a puzzle. For example, here you have Hashi, so it's a puzzle play in the edge. So this is the initial state. And as you can see, you have here some hits in some vertices. So that one is the vertex 0. So we have a mechanism to set the hints 3 to the vertices 0. And for this vertices, 5 to the vertices 2, etc., etc. So in the initial state, we can define all our hints directly like that in order to get the initial state. And a lot of constraints are referred only to a specific region. For example, for Sudoku, we refer for all the column, all the row, all subgrid. So in Ludii, we prefer to provide some shortcuts to define them, rather than describe all the different regions each time for each puzzle. So we have some different shortcuts like rows, column, diagonal, subgrid. So you have here the example of Sudoku. So for Sudoku, so here you have the design. Of course, this is a game of one player, so 1-1. For the equipment, we have, for the grid, a specific item called Sudoku board. We define that according to the number of subgrids. The variables are the cells of the board. Each variable, the value are between 1 and 9. And we need 3 regions, so 3 kind of regions, so we can define them directly thanks to our shortcuts. So columns, rows, and subgrids. You have here the rules of the game itself. So if you see start and that kind of stuff, this is an option. As I showed you during the experimentation, you can modify the size, you can modify the end. So we use that to define many options. And so for Sudoku, we can define many initial states, like all the puzzles. So from the same modulation, we just modify the initial state. So you have here an example corresponding to that. So the initial state here is just to set some variable to some value. For example, for this vertices, so 0, 1, this vertex is 1, we set the value 9. For these vertices, the value 4, etc., etc. And from that, we get all the initial states. And on the rules, this is really easy, like I said. We have one region to define all the constraints. For Sudoku, so we have the plain rules, we have to satisfy the constraints, modeled by only one specific constraint for these puzzles. It's all different. All the value of the same region have to be different. And the regions are all different for each column, all different for each row, all different for each subgrid. And like all the puzzle, if you solve the puzzle, you win. So in that case, if you reach a state where the puzzle is solved, you win directly. So I just would like, I have time to show you. I just would like to show you one resolution in Ludii directly, and Cédric will explain to you how that works. So Sudoku. I set the CSP solver, and I can run it, and it solves directly. So you see all the possible value evolve are automatically done. And just a quick one, I'll stop that. So Philopix is another puzzle and you can play online, it's very famous. You will see. A CSP can draw. Up, it's solved automatically. So I don't explain how that works, this is not my work, it's work. So, up. Yeah, okay. So how we do this? We use control programming, and before that, a little word about AI for general game playing. There is nothing new for you, but clearly, in general, what is considered the best is the Monte Carlo research. You know that, nothing new. But in the specific case of puzzle solving, we tried MCTS, and it's really bad. It doesn't work at all. Yet, logical puzzles, they really often rely on very limited set of mechanisms, you know, and a lot of them it's really similar. And constraint programming, you may not be familiar with constraint programming, but it's a field where when we want to exhaustively explore a combinatorial space. So it's a heavy task in general. But there is a lot of improvements last decades, and
I don't know, in the 19s, for example, we can only solve toy examples, okay, because combinatorial space. But now in practice, we have application and we can solve some instances really huge from various applications. And what we do is filtering. We love to filter. This is our thing. And we have a lot of propagation techniques that really fits. It's really similar to the puzzle mechanisms I'm going to show you. So the idea is to use this technology to solve puzzles very quickly, ideally. And how do we do that? We use a format which is called XCSP, because one possibility would be to use directly a solver. We have CP solvers. We can plug a CP solver to Ludii, and it's okay. But the problem with this is you would be stuck with just one solver. What we want to do is be able to use as many solvers. There are tens and tens of solvers around the world, and researchers who work on this topic. And with this format, you can use as a black box, and not any solver, because some of them don't support this format, but there is a competition every year, and you have major solvers, they all read XCSP, so you are not stuck with just one solver. This was just a little technique thing. I'm not going to talk about the gory details, the algorithm of filtering. I'm sure it doesn't interest you. But, okay, this is a screenshot from Nicoli website, and there are logical puzzles, and many of them are in Ludii. What we could have done is, okay, I have a Sudoku, I can translate Sudoku in XCSP and solve it, and I can do for the second one, the third one. But this is not what we wanted to do. We want to translate mechanism in a way. If you have the same mechanism in a new puzzle, you don't have to do anything, the solver will do it for you. You know what I mean? We don't translate a puzzle from Ludii to XCSP, but just mechanism. In more detailed way, for example, just the first one with Sudoku is all different. This is a starting board for Sudoku and the solved one. In Ludii, Eric show you, it's a whole different, and this is very similar to a propagation algorithm which has been proposed in '94 by Jean-Charles Régin, which is called All Different Constraints. And what is tricky in this work, but what is nice, is the whole different can stand for different things. Here it's for integers, okay? You have a height here, so you cannot have a height in this line, this column, and in this subgrid. But for example, if you have all different for binary, it's another puzzle. And the whole different doesn't stand for an element, it stands for a line. It means you cannot have two lines which are equivalent, but you can have 8, it's not 8, it's 0 and 1, but you can have, the element can be the same, but not the entire line. So it depends on the context, and we translate the mechanism in general. It can be elements, it can be integers, it can be lines, or even matrices. Okay. This is for the first mechanism. This is a quick explain. Of course, I don't speak a lot of this presentation because it's not. I don't think you will be very interested by that. But this is a translation in the format, and after that you feed the solver with that, and it's solved. Okay. This is another mechanism which is really. We meet him a lot. It's when you have to count or place elements with respect to their sum, like you may know square row, magic square is very famous, and here kilobits. And for example, here it means that four neighbors have to be inked, filled. So there is 4. And this mechanism, again, it depends on the context of the puzzle, but now that this work has been done, if you define a new puzzle with this mechanism, we don't have to do anything to solve it. And this is also true I don't have example right now, but this is also true for other arithmetic operators, inequalities like Futoshi. Okay, Futoshi. Okay, another puzzle. Or projects modulo. I don't know any puzzle which use. Oh, maybe there with modulo, but you can do it. It's already done. One other is patterns. It's really common, really frequent in puzzles to have to follow a pattern. This is nonogram where you, for example, here 6-1 means that you have 6 color cells, then 1, but the 1 is not a neighbor. And in the beginning, everything is white. This is the solved puzzle. And how it's done, in CP we have another constraint which is called regular. And it ensures you a word is recognized by an automaton, okay? And you can filter, for example, this is the first line. There is 2, then 2. So 1 is the cell is filled, 0 is empty. Okay. So you can have any empty cells as you want, no problem. As soon as you have one which is filled, the next one is also equals 2. Okay. After that, you need to have an empty cell, as many as you want. But you also, when you meet the next one, you know there is also another one after that, and at the end. You can have as many zeros as you want. This is a general pattern, so it can be applied to various puzzles in general. Yeah, sorry. I think I'm in the end. Yeah, this is quick results. This is the results from the paper. Okay. Now they have been improved. And we were discussing, do we present the new result of the paper one? This is the paper results, but it's in general really quick. You can solve puzzles within a few seconds, and now within less than 1 second now for most of puzzle. I quit. Okay. Conclusion. XCSP and the solver in CP technology brings to Ludii a powerful solving process for puzzles. In exchange, Ludii brings to us new instances, which is always nice because we like to have new problems to work with. And in photo work, there is some mechanisms we are working on, like cycle and connectivity between regions or edges. We would like to work on generation of puzzles and maybe hybridization with machine learning, which is really not for now. And thank you for your attention.
Rubik's Cube is also a logic puzzle in a sense. Would it be possible to code it in Ludii or solve it with XCSP?
Yeah, in general it's possible, but Rubik's Cube is, we focus now on NP-concrete problems. You know, Rubik's Cube is like Soemers, it's piece-based problem, but yeah, it's possible. But not for now, we haven't done it.
But you have a huge number of states, I mean, it's not easy.
Absolutely, but there is some constant programming work for Rubik's Cube, and there is a lot of symmetry. In this result, we didn't use any symmetry. We are like unaware of what we want to solve. So we don't use any specific techniques for solving. It's really general. Okay, but for Rubik's Cube or some puzzles, you can use techniques to improve the solving process.
Yeah, we can model them in Ludii. Of course, we have to make a specific way because it's Ludii. But yeah, we can model that. You can translate that in a program, but if you solve it without any heuristic, without use any symmetry or nothing, that's a shame.
So it's tangibly related, but so if you're using CSP for the puzzles, by translating it into a basically competition format, have you thought about doing the same thing for your non-puzzle games with planning? So converting into puzzle and using standard planners.
That's work in the pipeline.
It's a preliminary work, so maybe we can exploit this.
All my thesis is on that. I use CSP and MCTS. I translate some stuff from SCSP, so stochastic constant programming. And from that, I combine constant programming and Monte Carlo techniques. And my algorithm is one of the best complete.
Yeah, it was one strength of Woodstock.
If you look at all stuff with GDL, it's a really ugly thing. Currently, I'm the winner of the selection with that.
Okay. Thanks. And our final speaker is a master's student from Maastricht University, Lianne.
Are we going to use this?
Okay. Go back.
Hello, everyone. As has just been mentioned, I am a master's student at Maastricht University, and I've been involved with the Digital Ludii project for the past half year. As the title already indicates, I've focused my efforts on logic puzzles, and specifically on creating a functional taxonomy that eventually allowed us to implement all the nice features that the others have already explained in the Ludii system. I have mostly focused on a group of puzzles that is known as Japanese logic puzzles. A couple of them have already have already been mentioned, including the all-famous Sudoku puzzle. These puzzles have a couple of characteristics which I will mention before we move on. First off, it's a single-player game, as are most puzzles. They all have simple rules, and they are language independent. Now, this last part is really important because this group of games doesn't need any translation. The rules might need translation, but the puzzle itself doesn't, which is why this is a very important point in the list. Then there is, all of them are solvable by deduction, which the name logic puzzle already indicates, and there is a gradual increase of information by the solver during the process of solving this. As you start, you don't have any information except what is given, and as you move on to the solution, you will gain more and more information and finally solve the puzzle, if all is right. Another important point is that these puzzles have one unique solution. It's a bit of an honor rule for the makers of these sorts of puzzles. Every single, individual instance of a puzzle should have only one solution. This is the resulting taxonomy. Notice that I did renaming of the Japanese logic puzzles name, because the category is descriptive but not really useful, because there are many more publishers and not just the market dominating Nicoli that publish these sorts of puzzles. As such, I've renamed it the Abstract Logic Puzzle Group. There are three main branches. I'm just highlighting them at the moment. I will go over this taxonomy in the following slides. Now, first off is the path category. It focuses on paths, connecting elements within the puzzle. By the way, I forgot to mention, this taxonomy is based upon goal. The goal of the puzzle. That's how they are categorized. So all the puzzles in this group deal with connecting elements within the area that you have available. I'm giving examples of each of these categories for all of the main groups in the taxonomy. So first off is the connection group, which is pretty easy. This is the Hashi puzzle. You've already seen it. Basic idea is connect all the circles with straight lines. There can be only two at most. This is one of the simplest puzzle types. It's just drawing lines, creating paths. It's really easy to recognize. But when it gets a little more complicated is when the paths are supposed to close in on themselves, like Uberus, the snake that eats its own tail. There can be more than one loop, and sometimes the loops can cross. But this is a different type of puzzle, although it still fits within the path category. Massieu is an example of that, where you have to go through all the different circles in the right way and finally close on itself. Adding direction means that you got another type of puzzle. This is just Nabe, with a puzzle that requires you to put all the, well, let's just call them balls, to another part of the puzzle. This adds direction to the paths and is thus distinct from the other types. The position category is a much more complicated collection because it deals with location. The position of the elements or the position of the values is of utmost importance. Starting off, you've got the symbols category, and subcategory you can have ordered or unordered. I'm hoping this is visible, but the puzzle that was mentioned before with the unequal signs, that's this one. The unequal signs must be followed, but otherwise it's just like Sudoku. Fill in the numbers, make sure that every row and column only has one of each number. And this is a puzzle named Juosan. I'm fairly sure that most people will not have heard of this because, yeah, it's not that well known. And this one uses lines. However, it's not a path puzzle because these lines don't form paths. They're not meant to be paths. The only thing that this puzzle worries about is how many of them there are in the region. I'm going back for a moment. See, these blocks of cells are regions, and they only care about how many of the horizontal or vertical lines you put in them. Thus, it is treated as a symbol and goes into the symbols category. Futoshi Key makes use of the ordering, hence the unequal signs, but Juosan doesn't care about that, which is why it goes into the unordered category. Then there is the shapes category. The shapes can be mixed. They can have any sort of variation, or they have as part of their rule set that the shapes must be somewhat similar in shape. Tantaisho requires you to have symmetrical shapes, but Shikaku requires you to have rectangular shapes. Then there is the shading category, or as you could also call it the color category, because this one deals with colors, just colors. Hitori is a puzzle where you have to fill in some of these numbers. You start out with duplicates, I hope it's possible to see it, but the duplicates must be eliminated by putting in the black cells. And the focus here is on the white. The idea behind background-foreground naming is that the background is the white of the paper, because all of these puzzles are generally pen and paper puzzle games. They are published on paper, so the white of the paper would be the background, and the black of the cells filled in with the pencil would be the foreground. There are puzzles that do the other way around. Nurikabe here wants you to put a wall of black cells creating little islands of white cells. So the focus here is on what you're actually filling rather than what you're not filling. And, well, it's not working. And some of these puzzles say, well, I'm not going to do either of that. You will need to balance the white and the black, or whichever other color is used in here. And this is not technically a pen and paper puzzle. However, since there are puzzles with two colors, it stands to reason that there are also puzzles with more than two colors. So the category is there, although I don't technically have categorized any pen and paper puzzle. This one is from the Simon Tatum online puzzle collection, but I'm sure there's many more variations you can see. it's the exercise where you have to color in all the different regions, and regions that are neighbors to each other can't have the same color. Now, as for the distribution of the different puzzle types, I classified 100 puzzles using this taxonomy. You can see the distribution, yeah? Okay, I'm hurrying. You can see the distribution over here. Interesting to note is that although there's a lot of difference, it's mostly the position category that ends up eating most of the puzzles, claiming most of the puzzles. It's likely because it offers more options, more possibilities. Now, I actually had another part scheduled for describing Sudoku, but my colleagues already took care of that, so I'll just be moving on. Thank you.
Probably one question. Good. So Eric and Matthew will just give a quick demo.
Yes.
So just, I would like to explain the rules of Amazon for the people that don't know. Just a second. So that game is Amazon. You have the initial state there and the terminal state there. So it's a game played in a chessboard of size 10. You have 4 queens for each player. You have 2 turns at each, like two kind of move at each turn. The first one, you can move the queen exactly like chess. So I think if anyone knows chess and you move anywhere you want in each direction. And after that, where your queen is, for example, there, you can shoot a dot like that to any position where she can go to any empty side. Okay? And the goal is to block your enemy. If your enemy cannot move, he loses. So if he's stalemated, he loses. So let's go to make that game with Ludii. So you have my nice Eclipse. So we need to create a file with an extension .lud. So it's an example. Up, so I will make that. In Ludii, you have to describe the Ludem game to create your game. On it, you have to describe the name of your game. Here it's Amazon. We define our game with 3 parts. The first one is mode for the number of players. The second one is the equipment of the game. And the last one, the rules. Oops, I close my game. So now, one by one. So how many players for Amazon? 2. Up, mode is finished. Now we have to describe the equipment. For the equipment, we have, of course, the board of the game. The board. What kind of shape? A square shape. Of what size? Size 10. So square, size 10. What kind of tiling? Square tiling. Up, my board is defined. What kind of equipment I need? I need 1 queen. For who? For each player. And each queen can shoot a dot. So I need a dot. But this dot is not from any player, it's for no player, so it's for the player none, for no one. Okay? Here we have all the equipment we need. So we have the board, the queen for each player, and the dots. So I would like to just compile that for you, but I need some rules to compile to verify if the game is valid or not. So the starting rules are optional, of course, but I need some playing rules. You will see after I need by pieces is to define the movement of each pieces. So for now it's by pieces, but each pieces are no move. It's just to get some playing rules. And I need some ending rules. So like I said, the goal is to stalemate the opponent. So if the opponent, the next player, is stalemated, what is the result? The current mover wins. So I describe my game exactly like I understand. So I can compile that if I don't make any mistake. I hope. Last one. Yeah, great. So you have for now you have that. So it's just a board with nothing on it, just the board, the correct size. Now I have to define the initial state. Where is the queen? For that I have many options. I can define thanks to the cells, the indices of the cells, or with the axes. So for this example, I prefer to use the axes. The axes. So yeah, we have a queen. We have a queen in a4. We have a queen there. A queen there. So I can use this coordinate to describe my game. So I just close that. I go back to my description. So now I have to define my initial state. So the initial state is done by the redeem start. We have to place our queen. So you have to place the queen according to their name. So the default name of a covenant is the name of the redeem and the ID of the owner. So you have queen 1 for the player 1, queen 2 for the second player. So queen 1. And after that, we just have to specify all the coordinates of all the initial queen. So logically, you look your board with where you want to put your coordinate. Of course, I know them for that. So up, and you do exactly the same for the queen of the opponent, the second player. Up, A7, D10, G10, and G7. Up, and from that, if again I don't make any mistake, if I recompile, yeah, I have my queen. So my initial state is done now. Of course, no move for now. If I try to move, all of the moves are illegal. So I have to define the move. So like I said, we have two kind of move at each turn. First one, you move the queen. Second one, you shoot. So first one, I will define the movement of a queen. So here we have the by-piece redeem. So I can define a generator of move for each queen. So here in the covenant queen, I can define the move of each of the queen. So we use the vocabulary of the chess again. It's a fairy chess if you look online. So the movement of queen is a slide. You can slide, but you can slide where? Only if this position is empty. So if the 2, the place where she go, is in the empty site. Up. I think it's okay. So just that is enough to define all your movement of your queen. So I have to recompile. If I recompile, I print the legal move. Yes, I can move my queen like chess. Okay. Of course, for no shoot. That thing is done. Now I have to specify the shooting move. So each time you move your queen, the same player has to replay to shoot. So the consequence of your queen move, so to slide, then to define the consequence is to replay. Okay? If I slide, I replay. After that, I can define in the playing rules the second kind of move. So if the turn is even, so 0, 2, 4, etc., I have to move my queen. If this is not even, I have to shoot. So I shoot, like I said. I shoot exactly where can go the queen. So it's exactly the same thing like a queen. And what kind of thing I shoot? I shoot a dot. But this is on by the player none. The ID of the player none is 0. So I shoot a dot 0. I shoot. Okay. I shoot in all the directions, of course, like a queen. I compile, and this time I have the complete game, so I can shoot from my queen. All the rules of Amazon are on it. I write the game exactly like I understand the rules. Just now is optional, like we said before, I don't remember who, but someone asked if we can make something specific GUI directly from our game. Yes, we have that. So just initial state. I go back to my description. Here, as you can see, we have the board, the generic board with the shape tiling. But to get the nice GUI of Matthew, as you see in his demo, I can use a chessboard. By default, is a square shape and a square tiling. So I just have to define the size. Here is a size 10, and this is done. If I recompile the same file, I have my and it's finished. So here you have all the description of Amazon, exactly like we understand the game itself. So now, let's Matthew.
Yep, the session's officially over, so but Matthew will do a quick demo if you want to stay behind. I can do it really quickly.
So we can just show off some of the games that we have. I think as I mentioned before, Stephen's a bunch of games. So we have a game like Reversi, which is a scoring game. So we can do games with scores. We can do stochastic games like backgammon, for example. Yes, yeah. So we have games with stochastic elements on them. We have games with hidden information. So, for example, a game like Stratego. So if you place your pieces on the board, they then become invisible to the other player. And you can actually play this game over a local network. And if you play over a local network with 2 computers, each computer can only see the information that that player has. So all the hidden information that should be hidden from them is hidden. We have many other types of games. We have simultaneous move games like rock, paper, scissors. That was a draw. That was a boring game. We have graph games. So, for example, dots and boxes. What other games should I show? Laska. We have stacking games, which is a leaping game. Thank you. So the pieces in this game are stacked on top of each other. We have that capabilities. We have puzzles, as we've seen before, but I can just show the interface for it. Something like Sudoku. So we have some nice little features for puzzles. You can see that each square has the legal moves that cell can take. So you can easily select the values that you want. Anything else?
Tron.
Tron, yes, a real-time game. So we have some primitive real-time game capabilities at the moment. Like I said, the focus is on traditional board games, but the Ludii system is flexible enough that it has this capability as well. The agents aren't very good though. Anything else? Mancala, yes, a board game with a unique board.
And the track.
And it has a track as well. So this game has a custom board for Mancala style games, and this game also has tracks that the player has to follow. The players have to move their pieces in a anti-clockwise fashion around the board. You have a question?
So you share so far the web page, the YAR file, but it's not open source yet.
Not at the moment, no.
So you will not make it open source? You will,
maybe next year when the source is more stable, when it's more complete.
Yeah. For this version, open source is not necessary because we have to improve too much things. So the code itself has to be improved again for the game description.
Yeah, I understand.
So for now, next year.
I just wanted to know what the plan is when everything is stable.
No firm plan yet, but maybe next year.
The plan is to make it then
Yeah.
open source.
Right now we're just right now we're making too many changes with the language. We'll just change too much.
For the for the real-time games, are they locked to the decision-making time of the agents, or are they actually running in real time? So, what I mean is like, do the agents, the AI agents, have to return a decision order for the rest of the world to, like, carry on moving basically, or does it actually run in real time, regardless of what the agents do or the player does?
I think I don't remember for sure, but I think it will just keep moving on. We don't yet have a mechanism to actually inform the agent that we already moved on, so then it might still return like it's moved from the previous state that it returned slowly. So yeah, this is very much a proof of concept. We're still looking into like.
I think if the agent doesn't make a move, it just applies the default move for that piece and just carries on going anyway.
And is there like a limit on how much thinking time there is in which we need to move at the moment, or is it still just sort of proof of concept?
Proof of concept, you can speed it up or slow it down as much as you want, but however fast you want to make a tick.
Cool. Okay.
Yeah, it's 40 or 60 milliseconds currently.
Like something like the GVG AI.
Yeah, something close. But you can just change one parameter. If you wanted to make it really fast or really slow.
Alright.
Okay. Yep.
Card games?
Card games? Yes, we have card games. Just one at the moment. Not a very good card game. Very simple card game. But yes, so we have, for example, this game with hidden information. We have the decks in each player's hand. This is a war game. It's called War, but it's a very simple card game. So yes, we have the capabilities for card games. And yes, for the full release, we will add a lot more solitaire, pre-sale, all these card games.
Okay,
Poker, yes.
Yep.
How long are you working on that project?
It's a 5-year project. We're at the 1.5-year mark.
3-year?
5-year project. Yeah. So we'll probably develop the engine for another year or so, but it should hopefully be complete. And we'll focus on the historical aspects of it.
Yeah, that was actually my next question is, what are your plans for using this for, because I know, because it's a 5-year project, and you're looking at sort of ancient board games that you maybe don't know the rules for, if I remember correctly from last year. So how exactly are you planning on using this to help you? Is that for modelling the games, I'd imagine?
Yeah. Like we have partial evidence for a lot of games. The idea is that we'll model the known equipment as constraints in the system, and then leave the rules as free variables that the system can find similar rules from the similar time periods, similar cultural contexts, similar locations. So we have these plausible rule sets, and then we can do the self-play analysis to check whether these games actually work. And we're trying to maximise the historical authenticity with the quality of the game.
For example, there was one translated rule description for this game, Ludii, and it turns out that actually it was mistranslated, and then if you run this to an algorithm, the AI wins immediately on the first time. So you can do, so that's obviously a really simple concept, but yeah, you can do AI analysis to check that.
Yeah, for motor.
Maybe they didn't play it this way.
We tried. It was really fun. If you want a rare one, it's a bad one. Bad one.
So yeah, this is the original rules, I think, and you just
it's finished.
Game's over.
If you look on the book, it's like that.
For some of the early games, we have like 20 or 30 different reconstructions by historians which haven't been tested. So this should help us determine which are more likely to have been real.
Yeah. That makes sense.
Our expert of history is that. Us ours or kind of argument.